Welcome to our lecture on Pre-Calculus, Section 3.2, Polynomial Division. First thing we want to talk about is what is polynomial division. So it's stated in a theorem on polynomial division. So it says, suppose d of x and p of x are non-zero polynomials where the degree of p is greater than or equal to the degree of d. There exist two unique polynomials, q of x and r of x, such that this equation holds. P of x is equal to d of x times q of x plus r of x, where r of x can be 0, or the other possibility is that the degree of r must be less than the degree of d. Okay, so let's talk about what these things mean. P of x is called the dividend, d of x is called the divisor, q of x is called the quotient, and r of x is called the remainder. Now let's think about these in terms of a problem using numbers. So let's go way back to when you first learn how to divide numbers using the long division algorithm. Okay, so we learned these words way back then. And since then, we've kind of stopped doing it by hand for the most part and gone to using the calculator, so this skill is rusty. So we got to bring back some old ideas here. So you've got this bracket here that we write. Underneath it is what is called the dividend. And then in front is the divisor. So the divisor is dividing into the dividend. Your answer part is called the quotient. That's how many times the divisor divides into the dividend. And then whatever is left over after you carry through the algorithm, subtracting all the way down, is called your remainder. Okay, so what this over here says, the dividend, that means the polynomial that you're dividing into, is equal to the divisor, this part out here, times the quotient, this part up here, plus the remainder. Now let's see how that looks with real numbers. Okay, so I wrote down this little problem here, 5 divided into 107. So 107 is the dividend and 5 is the divisor. So using our algorithm that we learned way back, we're going to say 5 goes into 10 2 times. I'm going to write the 2 over the last digit in the 10. 2 times 5 is then 10. And then we subtract 10 from that 10 on top and we get 0. And then we bring down the 7. We don't have to write the 0 in this spot here, but we then would bring down the 7. 5 goes into 7 one time. I write it over the 7. 1 times 5 is 5. I put it under the 7. And then I subtract the 5 from the 7 and I would get 2. All right, now if I set that up in this setup right here, let's see how that would make sense with this problem here. Okay, so this says here that that the dividend in my number problem is 107. The dividend is equal to the divisor. The divisor in my problem is 5, multiplied by the quotient. The quotient is your answer that goes on top. So 21 is my quotient. And then add to that the remainder r of x. Well, this is your remainder here at the bottom. Your remainder is 2. So add 2. All right, and let's see if that's true. So 107 should be equal to 5 times 21, which is 105, plus 2, which is equal to 107. So that's definitely true. So we've made sense of this long-looking polynomial equation here in terms of the algorithm which is used for real numbers. And we're going to learn right now how to do that with polynomials instead of real numbers. the idea of the fact that the remainder could be 0. Well, if this was 105, for instance, it would go in evenly 21 times, and you would have a 0 remainder. That's the understanding. If you are able to divide a polynomial into another polynomial and not get any remainder at all, that means that polynomial divides evenly into the dividend polynomial, and that means you would have a 0 as your remainder. Okay, now let's learn how to do this with polynomials. So we're going to do this simple example here where we've got the polynomial p of x divided by the polynomial d of x. So it would be written like this. So we put the divisor out front and we put the dividend underneath like that. Now the steps that we take are we want to ask ourselves, how many times does this first term x go into this first term x squared? So what you're really asking yourself is, what do I multiply x by to get x squared? Well, the answer is x. So x times x is x squared. X squared goes under x squared. Those terms will look exactly the same. All right, so now we say x, now we say x times -2 is -2x. We're going to line that up under the other x term. So -2x goes here. Now we want to subtract that. So notice it's very similar to the real number example. We're on the subtraction step now. So x squared minus x squared should be 0 because these terms are always going to match here. It's the way we set that up. 3x minus -2x is 3x plus 2x, so that's 5x. And now we bring down another term, plus 8. And we go through this process another time. What do I need to multiply x by to get 5x? So we say 5, and we write it up top. So 5 times x should be 5x. And then 5 times -2 is -10, and I line it up under the other constant, 8. Okay, now I subtract. And I get 5 minus 5x is, of course, 0, like we expect. 8 minus a -10 is 8, plus 10 is 18. Okay, now you check to see if you're done. The degree of 18 is 0. The degree of x minus 2 is 1. This degree 0 is less than this degree 1. When that happens, then this is your remainder. So our remainder is down here, 18. So now we want to put it in the form specified in our polynomial division theorem, this right here. We want to go ahead and put it in this unique equation format. All right, so this is the form we want to put it in. So let's identify which piece is each of those. So this is p of x underneath. This is q of x on top. This is r of x on the bottom, and this is d of x in front. So p of x, x squared plus 3x plus 8 is equal to d of x, x minus 2 times q of x, x plus 5 plus 18. And this is what we're looking for. This is the unique equation that we can set up when we have x minus 2 as our divisor and x squared plus 3x plus 8 as our dividend. So we've done it, and this is what we're looking for. All right, let's look at the next theorem. This is called the remainder theorem. And this says, suppose P is a polynomial of degree at least 1. So in our case, our polynomial is this, so the degree is 2, so that qualifies. And C is a real number. All right, so when P of X is divided by X minus C, so we're dividing by X minus C, so X minus C, so in our case, C is 2. So the next thing it says is when P of X is divided by X minus C, the remainder is P of C. So what P of C means is that you substitute your number C into the polynomial P, and this theorem is telling you that you should be able to figure out the remainder by doing that without going through the whole division process to get that remainder. So let's see how that works out. So we already carried through the division, so we know we're supposed to get 18, because that was what R of X turned out to be when we carried through this division. But let's see if it works if we find P of C. So that means I'm substituting 2 into my original polynomial, and I'm expecting to get 18. So I'm substituting 2 here. So I got 4 plus 6 plus 8, so that's 4 plus 14, so that's 18. Okay, so it worked. So that this theorem is true. As we can see, it worked for this one, but it will work for anyone. That's what a theorem tells you, that it's good in any case as long as the conditions are met. So just to illustrate exactly what we're saying here, whenever you've got a polynomial of degree at least 1 and C is a real number, if you divide by this little linear polynomial x minus a real number, your remainder can be calculated without doing your division steps by substituting this number here, like this number here, into your polynomial, and you could figure out what your remainder is. So there's a lot of little neat things that come out of studying polynomials that are used in other branches of math, like cryptography and that sort of stuff. But we're just pointing out in this chapter some of the interesting concepts that come out of studying polynomials. Okay, next idea we want to talk about is the factor theorem, which says, suppose P is a non-zero polynomial, the real number C is a 0 of P if and only if X minus C is a factor of P of X. Okay, now this is going to help us in some of the problems we do in polynomial division in order to find zeros. So let's look at a couple of real number examples first to see what I'm talking about here. So if I divide 224 by 2 and I carry out the division algorithm, I'm going to find out that I have a 0 remainder. So that means 2 divides evenly into 224. So what that tells me is that 2 is a factor of 224. And what a factor is a number that multiplies by another number to get the number underneath. Okay, so we can see that that's true in this case. If you multiply 2 times the number 112, 2 times 112 is equal to 224, the number underneath, the dividend. So that means 2 and 112 are factors of 224. So we know that vocabulary word from all of our other math courses. When two things multiply together to give you a number exactly, then these are called factors of this number. And same thing over here. 5 times 21 gives you 105. You're not going to get a remainder if you divide 5 into 105. So what that tells you is 5 times 21 is exactly 105, and that you will not have a remainder, and that those two numbers, 5 and 21, are called factors of 105. Okay, now the same thing holds for polynomials. if I divide x minus 2 into x squared minus 6x plus 8, let's just carry it out. So we're going to follow the algorithm. X times x is x squared. X times minus 2 is minus 2x. Now we're going to subtract. So we'll get 0 in the first location. Then we'll have negative 2 minus negative 2x. So that's negative 6x plus 2x. And that'll get negative 4x plus 8. All right, so we keep going. So x goes into, what do we have to multiply this x by to get negative 4x? So we ask ourselves that. So the answer is negative 4. So negative 4 times x gives you negative 4x. And negative 4 times negative 2 gives you positive 8. So you could see that when you subtract these two, you're going to get 0. Okay, negative 4x plus 4x is 0. 8 minus 8 is 0. Okay, so that pattern follows here. So I've got a 0 remainder. So what the factor theorem tells me is that if this case is true, let me just write it out. If x minus 2 times x minus 4 is exactly equal to x squared minus 6x plus 8, which it is because I have a 0 remainder, then these two right here are factors of this polynomial. That makes sense. We know that's the case in our other studies of math. So that tells me that according to my factor theorem, if x minus c is a factor of p of x, here it is, it's a factor of p of x, then c is a 0 of p of x. Well, yeah, we already kind of know that. If I want to find a 0 of x squared minus 6x plus 8, and I know that these are my factors, then I know that the 0 for this factor is 2, and the 0 for this factor is 4. Okay, so that just lays it all out in terms of the vocabulary we're using in the polynomial division chapter. Let's do a couple more examples here. First one I'm going to do is number 1. And what we're going to do is we're going to write it in this form here. So I'm going to set up my algorithm. So my divisor is x minus 3. And that's divided into the dividend, which is 4x squared plus 3x minus 1. All right, so following my steps, what times x would give me 4x squared? So I'm going to write that up here. So it's 4x. 4x times x gives me 4x squared. And now distributing 4x times minus 3 gives me negative 12x. Now I'm going to subtract. So I should expect to get a 0 in the first term because that's why I chose 4x as part of my quotient. Now I've got, I've got 3x minus negative 12x, so that's 3x plus 12x, so that's 15x. Now I'm going to bring down my negative 1. Okay, let's do it again. So x times something will give me 15x. Well, we can see that it would have to be positive 15. So 15 times x is 15x. 15 times negative 3 is negative 45. And then I subtract. So I've got 0 here like I expected to get. Negative 1 plus 45 is 44. So my remainder then is 44. Now I'm asked to write it in this term, in this fashion. So I'm going to say p of x. P of x is my polynomial, which is my dividend. So 4x squared plus 3x minus 1 is equal to d of x. D of x is my divisor. So d of x is my divisor, x minus 3, times q of x. Q of x is my quotient on top. Plus 44, which is my remainder. And this would be what my answer would look like. And that is uniquely the way it would work for this divisor x minus 3. Okay, this is the unique equation that you'll be able to determine using the divisor x minus 3. So we can tell that these two are not factors of this polynomial because this right here is a non-zero remainder. Okay, so those are not factors. All right, let's do another one. Okay, we're going to do problem number 4 now. There's a couple of points we need to make about this problem. So I'm going to set it up. I'm going to say x cubed minus x squared plus 1 is my divisor out front, divided into the polynomial negative x to the 5th. Now notice that there's not an x to the 4th term, so I need to put a placeholder term in there, 0 x to the 4th, in case I need that column. And then I've got 7x to the 3rd, and then no x squared term, so I need to put a placeholder for the x squared column. And then I have minus x. And I do not have a number in the constant column either, so I'm going to put a placeholder there. All right, so I'm looking at this and I want to make sure I'm not missing any of my powers. 5, 4, 3, 2, 1, and constant. In case you need those columns, make sure you set it up like that. All right, so now we want to ask ourselves, what do I need to multiply x cubed by to get negative x5? So that would be negative x squared. So negative x squared times x cubed is negative x to the 5th. They have to match. Negative x squared times negative x squared is positive x to the 4th. And negative x squared times 1 is negative x squared in the x squared column. And we'll subtract. So we have 0 in the first, x to the 5th column. So here, 0 minus 1 x to the 4th, so that would be negative 1 x to the 4th. I don't need to put that 1 there. 7x cubed minus 0 would be 7x cubed. And 0x squared minus a negative 1x squared is plus 1x squared. So I don't need to put my 1. Then I'll bring down my next term from top row minus x. All right, so now we'll do the steps all over again. So what do I need to multiply x3 by to get x4? Negative x4, actually. So that would be negative x. So doing the multiplication, negative x times x third is negative x to the 4th. Negative x times negative x squared is positive x cubed. Negative x times 1 is negative x, so it has to go in the right column. So that means there's nothing in this spot. All right, now we'll subtract. So, of course, in the first column we'll have a 0. So we have 7 minus 1 x cubed, so that's 6x cubed. And then x squared minus 0 is x squared. And we have negative x plus x is 0. So this is 0. Now there's really nothing to bring down here, so let's just erase that. All right, so these two, x3, same as x3, so we need to go all the way down to 1 degree less in order to say we're finished. So let's go through the steps one more time. So what do we need to multiply x3 to get 6x3? So that would be 6. So we have 6 times x3 is 6x3, just like we want. 6 times negative x squared is negative 6x squared in the x squared column. 6 times 1 is 6. Now we subtract. So in the first column we have 0 as expected. 1x squared plus 6x squared is 7x squared. And 0 minus 6 is negative 6. Check the degrees to see if we're lower. So here x squared, here x cubed, we're lower, so we're done. So this is r of x down here. This is d of x. This is q of x. And this is p of x. So we'll write it in our equation form. So we're going to say p of x, which is negative x to the 5th plus 7x to the 3rd minus x is equal to d of x, which is x to the 3rd minus x squared plus 1 times q of x, which is minus x squared minus x plus 6 plus r of x, which is 7x squared minus 6. So this is the equation we are looking for, the unique equation for the setup we have given here. Okay, we're going to do one more here. We're going to do number 6, and that should give you the idea, enough information to do these. So let's scoot this up. All right, so I've got x squared minus 1 out front, my bracket. Then I've got 4x squared minus x minus 23 underneath my bracket. That's my dividend polynomial. So this is my divisor polynomial, my dividend polynomial. We're going to find out the quotient and the remainder. Okay, so I've got x squared, then I've got x, and then I've got a constant. So I don't have to create a spot. I've got all of my degree terms represented. All right, so let's go ahead and do it. So what do I have to multiply x squared by to get 4x squared? Okay, so that would be 4. So 4x squared is 4x squared. 4 times negative 1 is negative 4, so that's a constant. I'm going to put it in the column with the other constant. Now I'm subtracting. So I'm going to get 0 here. Negative x is just negative x minus 0 is negative x, and then I've got negative 23 plus 4, so negative 19. All right, now I'm going to examine this and see whether I need to do another step. So notice the power of this term is 1, the power of this term is 2. So when that occurs, that means you're finished. There's not another step. So this is going to be my remainder right here. So I'm done. Okay, so I'm going to write it out as in terms of p of x is equal to d of x, q of x, plus r of x. Okay, so p of x is my original polynomial, my dividend polynomial. Okay, so that's equal to my divisor times my quotient, just a 4. My quotient is just a 4, plus my remainder polynomial. All right, and so what you can see here is you have a non-zero remainder, so that means this is not a factor of this polynomial, otherwise this would be 0. Okay, so what else can we say? We can also say that this is the unique equation that can be determined using this polynomial as the divisor of this polynomial here. This is the unique equation. This is the only way you're going to come out with an equation using this as the divisor. Okay, so that's enough information on how to use the division algorithm. Okay, next thing we're going to learn is what's called synthetic division to perform polynomial division instead of using the long division algorithm, which I personally am used to because we didn't even learn synthetic division way back when I was your age. But now it's taught in most courses where polynomials are part of the curriculum. Polynomial division, that is. All right, so it's just based on patterns of coefficients, and somebody's devised this method so that you can avoid writing out all the x's. Some people like it. I don't use it that much, but it is part of what we're required to learn in this course. Okay, so the limitation is that the divisor can only be of the form x minus a constant. Okay, so you wouldn't be able to have an x squared or an x cubed divisor, only a divisor which was of this linear form. Okay, so we can see in example number 1 that this is x minus c, so that tells me that c must be 3 for this particular problem number 1. And our divisor is of the form x minus c, so we can use the algorithm called synthetic division. Okay, so the way we do it is we take our 3 and we write that first. That's our c number. Then we draw this thing, vertical line, and we leave some space, and then we draw this line. All right. Then we take our coefficients from our dividend polynomial, and we write them beside the 3 on the other side of the line. So the first one is a 5 for the 5x cubed. Then you need a space. Then a minus 2 for the x squared term. And then a 0 for the missing x term. And then a 1 for your constant term. Next step is you bring down the first number underneath the line. Okay, then you multiply these two numbers together. 3 times 5 is 15, and you bounce back up and you put it right here. Now you add these two numbers together and you put it underneath that column. Okay, now I do it again. We multiply 3 times the bottom number, you get 39, you bounce up and you put it next, like a zigzag pattern. Now you add these two numbers together and you put it down below. And we do it one more time. We multiply 3 times 39, and you get 117, which goes right here. You add these two numbers together, and you get 118, and that goes here. All right, once that last spot is filled, then you're done with the algorithm. Okay, so this right here is r of x. Right? So now, remember when we set this up, this was your x3 term, this is your x2, your x, and then your constant. Well, after you do the division, your quotient, which is going to be made using these numbers underneath, is going to be 1 degree less. Your quotient is always going to be 1 degree less, all right, if we're dividing by a linear factor, a linear polynomial. What I mean by that is x minus 3. If I'm dividing by a first power divisor right here, the degree of your quotient is always going to be 1 degree less than the degree of your dividend polynomial. Okay, so that means x squared, then this would be your x, and this would be your constant. All right, so my q of x, which is what I was looking for, is 5x squared plus 13x plus 39. My r of x is equal to that 118. All right. Then this is my p of x up here, and this is my d of x. So my unique equation that I can write is that p of x is equal to d of x times q of x plus r of x. All right, and this is the unique equation that I can get by dividing by x minus 3. All right, so let's try another one. Okay, let's do number 2. All right, so this is p of x divided by d of x, where d of x has to be of the form x minus c in order to be able to use the synthetic division. So if my d of x is x plus 2, then I want to rewrite it as x minus, so we have to have this minus here, so the c would be minus 2 this time. Okay, so that's your c. So c is minus 2. Right, so I'm going to put my c out front. My c is negative 2. All right, now let me erase this so I have enough room to do everything. So my c is negative 2. All right, so now I set up my bracket like this. All right, and then I put my polynomial in these spots here, putting in placeholder zeros where necessary. So I have 1x cubed, that's my highest degree, 0x squared, 0x, and then my constant is 8. Then I bring down my 1, and then I can start. So I got negative 2 times 1 is negative 2. Add negative 2 to 0, and I get negative 2. Do it again. Negative 2 times negative 2 is 4. 0 plus 4 is 4. All right, and then I do it again. Negative 2 times 4 is negative 8. I put negative 8 right here. 8 plus negative 8 is 0. Okay, so I've got a 0 remainder here. All right, and that tells me that my divisor x plus 2 is a factor of x cubed plus 8 when it goes in evenly like that. Okay, so if this term right here is the coefficient for my x cubed term, then since I'm dividing by an x to the first polynomial, we know that the highest power of the quotient is got to be 1 degree less, so that's x squared. This would be x, and this would be your constant. So q of x is what I have on the bottom. It's x squared minus 2x plus 4. R of x is equal to 0. Okay, now we want to write it in as this equation, this unique equation that we get when we divide by x plus 2. So I've got p of x, that's x cubed plus 8, is equal to d of x, that's x plus 2, times q of x, which is x squared minus 2x plus 4, plus r of x, which is 0, which I'm not going to write. Okay, so that means these are factors of x cubed plus 8. And if I wanted to find my zeros, then I could find them from my factors. Okay, so that's the other theorem we learned. If I want to find my zeros, then these two polynomials that I found would have to be factors of the original polynomial. Okay, we're going to use that idea a little later. Okay, we're going to do one more of these. This one can also be written with a divisor polynomial, which if you look at it here, it's 2x minus 3. It's got that 2 in front. It's supposed to look like this, x minus c. Okay, so there's a technique we need to use in order to get it in the right form to use synthetic division. So let me write it out here. So I've got 4 minus 8x minus 12x squared divided by 2x minus 3. Okay, so in order to not change the relationship between the two polynomials, if I want to get this 2 out of here by dividing by 2 here, I must divide all of these terms also by 2. Otherwise, I'm going to upset the balance of my fraction. I won't have the same fraction. All right, so I'm going to I'm going to write it as now 4 divided by 2 is 2. So this is negative 4. This is negative 6. And this is on the bottom x minus 3/2. Okay, so underneath here, this is where I want to have x minus c. So that means c is equal to 3/2. Okay, so I'm going to set up my synthetic division algorithm. Now let's be careful we get it in the correct order. So highest term of my p of x is negative 6x squared, then negative 4x, and then plus 2. So I'm not missing any terms, any degree terms, so I can say negative 6, negative 4, and then 2. All right, so I got to bring down my negative 6. All right, next I'm going to multiply 3/2 times negative 6. And I know some of you have either had me or Mr. Conley where we insisted that you do everything without a calculator. All right, so it's best to do it without a calculator so that you don't forget your skills. All right, so I got negative 9 here. Now I add those two numbers up, negative 4 minus 9, and I get negative 13. All right, now let's do multiplication again. Using this fraction, 3/2 times negative 3. So let's go ahead and write it out. 3/2 times negative 13. So that's negative 39 over 2. So let's write it there, negative 39 over 2. All right, so I'm going to add 2 and negative 39 together. So that's 2 plus a negative 39. So I've got to have a 2 in the denominator. So that's 4 over 2 minus 39 over 2. That's negative 35 over 2. And that's my remainder. So that means q of x is equal to 1 degree less than my original polynomial, which is an x squared polynomial. So this is an x term, and this is a constant term. So I've got minus 6x minus 13. All right? Okay, so we want to write it in this form. So I've got negative 6x squared minus 4x plus 2 is equal to d of x, which is x minus 3/2 times q of x, which is minus 6x minus 13, plus r of x, which is minus 35 over 2. All right, now what we want to do now is go ahead and multiply everything through by 2 to get it back into this original set of polynomials where your p of x looks like this and your d of x looks like this. So let me just clear some space here. All right, so I rewrote it so we had some room to work. So I want to get that 2 back, multiplying both sides by 2. So I can get it back in this original p of x, d of x form. Okay? Okay, so I wrote it out. We want p of x equals d of x, q of x plus r of x again. So let's go ahead and carry through that multiplying by 2. So that's negative 12x squared minus 8x plus 4. All right, so that looks like this now. Is equal to, so let's just put the 2 in with this one here. So I've got 2x minus, so 3/2 times 2, that's negative, is equal to negative 3. So that's 2x minus 3. Then we have this one next. And then, so this is all, let me just make sure you understand this. This is all one clump, all right? So if I'm going to multiply by this 2 here, I don't want to multiply it by this one and this one because there's no plus or minus in here. This is multiply. That means it's stuck together, sandwiched together. This is one thing, all right? But when I multiply it by that last term, all right, so let's move this out of the way here. So I am going to have to be careful that, that I distribute this 2 once to this clump and once to this guy over here. So we treat that clump as one thing. So I already multiplied the 2 into the first part of it. I already put the 2 in here. I would not want to do it here, or otherwise you're going to end up multiplying this by 4 instead of 2. All right, so now this one here, this 2, is going to be multiplied by this. So I've got 2 times negative 35 over 2. So that's just minus 35. Okay, so I've got it in the form I want it. This one is a little more complicated when you've got a divisor that looks like that and you have to get it in the form x minus c. There's the extra step of getting it back into the 2 original polynomials that you were working in. Okay, so that takes care of our synthetic division examples. Okay, so I'm not going to go ahead and do this example, but I just want to make sure it's clear to you that if you have a division bar, you've got the same setup, that you've got 2x squared plus 5 is dividing into the top polynomial. Okay, and that's because this is the same thing as saying that you've got 2x cubed minus 14x squared plus 7x minus 27 divided by 2x squared plus 5. Okay, so I don't think we need to do this example. There's nothing tricky particular about this process of using long division. But you're going to have to be really careful that you don't attempt to you cannot use synthetic division. Okay, so you cannot use synthetic division on this one. The question is, would you know that and why not? So pause this video for a second and think about why can you not use synthetic division on this problem. Okay, so hopefully you thought about it for a second and realized that your d of x is not of the form x minus c because it is got a power of 2. Okay, so you have to have a power of 1 in order to use synthetic division. So this highlights the fact that you cannot always use synthetic division as a shortcut if you've got a polynomial that is not of the form x minus c. So there is limited usefulness, which brings back to what I originally said as to why this wasn't taught in the early days of, well, I don't know if you want to call them the early days, but it didn't used to be taught. Okay, now this is a review from the last section. Write an equation for the polynomial graphed below. Okay, so what we're going to notice from this graph is that there are several real zeros. Okay, so here's a real zero here at x is equal to -3, and here's a zero here at x is equal to 5. So if we have a 0 at x is equal to -3 and x is equal to 5, then we know for sure that we have a factor of x opposite sign 3 and a factor of x opposite sign 5. Okay, because of the relationship between zeros and factors, opposite sign. All right, now let's look at the multiplicity idea. Okay, according to multiplicity, if you have this parabolic shape here where you bounce and go back the other way without crossing through, that means this has a multiplicity, this factor here has a multiplicity of 2. A multiplicity of 2 because we bounce or touch and we go back up like that instead of crossing through. All right, now as far as this 0 over here at 5, you can see the difference. This one cuts through in a linear fashion, like slicing through like a line. Okay, so that's a multiplicity of 1. Okay, so we know now that p of x, our polynomial, has got to have x plus 3 squared as a factor and x minus 5 as a factor. What we don't know is what the coefficient is in front. All right, so we need a point in order to figure that out. So I could see that I have a point here that'll work. So that's the point. X is 0, y is 90. So I'm going to substitute 0 in for x to figure out what that coefficient a must be in order to make this graph look like that. So I've got a times 0 plus 3 squared times 0 minus 5, which is equal to a times 3 squared, which is 9, times -5, which is -45a. Okay, and that has to be equal to 90. Okay, so -45a has to be equal to 90. So you can see that this is going to be 2, right? -2. So that means a is going to equal -2. All right, so I would put the -2 right here. Let's just write it in there. Save time, and this is my polynomial. Okay, that's a little bit of a review of getting the polynomial from a graph using the idea of zeros, factors, and multiplicity. All right, let's try another one. Okay, here's another review problem. So let's find the real zeros on this one. Real zeros are x-intercepts. All right, so here's one here at -3. So my zeros, my real zeros are at -3, 2, 5. So that means my factors associated with those zeros, opposite sign, plus, opposite sign, minus, opposite sign, minus. Okay, so then we'll look at the multiplicity. All right, so if it's a touch, the multiplicity will be 2. If it's a cross, the multiplicity will be 1. Okay, so for this 0 at -3, it's a cross, so multiplicity 1. At x is equal to 2, it's a touch, so multiplicity 2. And then at 5, it's a cross, so multiplicity 1. All right, so now I can write my polynomial. So I put a variable in here because I don't know what the coefficient is that's going to cause my peaks and valleys and my y-intercept to be correct. I need to figure that out still. All right, but I do know my factors are x plus 3 to the first power, x minus 2 squared, and x minus 5 to the first power. All right, now I need a point so I can substitute x and y in it and figure out what that variable a is. So x is 0, y is negative 2 will work. All right, so p of 0 must be negative 2. So that's equal to a times, I'm just going to write it out just to make sure everybody's 100% sure of this procedure. All right, so negative 2 is equal to a times 3 times negative 2 squared times negative 5. All right, so negative 2 is equal to 12 times negative 5. That's negative 60. All right, so then I'm going to divide. So a is equal to a positive 1 over 30. That's my coefficient that will cause that y-intercept to work, which would then also cause those peaks and valleys to end up in the right spot as well. So I want to go ahead and put that in here. Let me just go ahead and do this as quickly as possible. I'll just write it here. All right. So this is my polynomial with my coefficient 1 over 30 in front. So that's a positive coefficient. This is an even polynomial, so up, up, that makes sense. All right, so even polynomial, it's of the degree 2 plus 1 is 3 plus 1 is 4, fourth order polynomial, up, up, positive coefficient. Okay, everything works. Okay, last review problem, and I want to just reiterate the fact that that you shouldn't be taking any shortcuts on watching these lecture videos and taking notes, so that you have your notes ready for you right in front of you when you're doing your tests and quizzes, and so that you know the procedure I expect you to follow and how you would write everything down when I ask you to take a quiz, because those, of course, are all handwritten. All your steps are written out, and you know how the grading works on those because we've had several quizzes already. So these kinds of problems are most likely you're going to see again on your quizzes. So this one, let's look at the real zeros first. Okay, let's look at the real zeros so we can find the factors. So I've got one here at negative 4, here at negative 2. The resolution is off on this graph because of the cut and pasting. So this one is at 2, and this one is at 4, and this point here we're going to say is at 0, 30, my y-intercept. Okay, so my zeros, I have 4 of them this time, 4 real zeros, minus 4, negative 2, 2, and 4. So that means my factors from my zeros are opposite sign, and now let's look at the multiplicity. All right, so if it's a cross, then it's a multiplicity of 1. If it's a touch, then from what we know of so far, we haven't talked about any higher multiplicities other than 1 or 2. So there can be, of course, higher multiplicities, but we haven't tied that idea into how that would look on a graph. So we're sort of staying simple on these. All right, so this is a cross, so this is a multiplicity of 1, cross, multiplicity of 1, cross, multiplicity of 1, cross, multiplicity of 1. So all these factors have a power of 1, all linear factors. So that means my polynomial function, p of x, is equal to some unknown factor in front, which will give me that 0.0 30, x plus 4, x plus 2, x minus 2, x minus 4. All right, and we do know that the y-intercept p of 0 is equal to positive 30. All right, which is equal to a times 0 plus 4 times 0 plus 2 times 0 minus 2 times 0 minus 4. So 30 is equal to a times 4 times 2 times negative 2 times negative 4. So that looks like 8 times 8. So 8 times 8 is 64. So that means A must be equal to 30 over 64. All right, so that's a reduced 30 over 64. So 2 goes into that, and then 32. Okay, so it's equal to 15 over 32. So that's your A. All right, so that means P of x is equal to A. Let's go ahead and substitute that up here so we don't have to write it all out like we have been doing. So 15 over 32 would go here in front. That's your coefficient. All right, so my polynomial is highlighted in yellow, including my coefficient. All right, so that's all the review problems I want to do with you. You should have enough information to do polynomial long division, synthetic division, and then there's a couple of these review type problems in 3.2. As usual, if you have any questions about anything I've taught you in the videos, which I hope you're taking notes from, then just let me know.